hopefully you guys are feeling pretty optimistic of what we have here. We have a workflow that we can go ahead and train our predictor, train our word usage classifier right there. And we saw the improvements of why it's very useful to use a TF-IDF. However, perhaps we're going to consider different techniques we can improve our signal. You can imagine there is signal in our data set, so we want to amplify that signal and reduce some of the noise. Because we understand that we don't want our model to pick up on the noise, to pick up on the signal. So in this section here, let's talk about different ways we can improve our model signal. Now some of these approaches might have marginal effects in model's performance. In other words, incorporating them into our workflow might barely increase the model's performance. So when we talk about these techniques, we also got to consider, well, is it worth it? In other words, is it worth increasing model's performance if it means that it's slower to train or slower to interpret? Some of these are rather cheap. Incorporating them has no negative side effects, but we should consider that in our discussion of the following techniques. And that's why it's very important that we construct baseline models, that we incrementally improve our model by adding additional features to them, so we can see the progress of our model, understand how the increase of performance is going as we include additional features, additional parameters, or additional controls to our model. Now, we understood, we sort of brought up this discussion that words like the, a, and or are very common. And they don't really contribute much signal. In fact, they contribute noise because they occur in all types of documents. Documents referring to Python the programming language and Python the animal and any other type of task we're doing. They're just too common and there's not going to be much predictive power in these words. And since there's not much predictive power in these words, or negative predictive power, things that we don't want our model to pick up on, one thing is we might want to just remove them at all, remove them completely from our analysis. Let's not count these words. And yes, using something like the TF-IDF is going to reduce the contribution of these words because they're going to be very common throughout our corpus. Yes, their IDF score will be very small, so we're going to reduce their contribution. But let's take it a step further and just completely remove them from our analysis. The words that we want to remove from the counting process, from your analysis, in other words, we don't want these words to be features, those are going to be called stop words. And why they're called stop words? Well, the reason why I like to view why they're called stop words is because in the counting process, if we encounter this word, we should stop, not count it, and move on to the next word. So these should be a set of words that are very common that we don't want to include in our counting process. spaCy has a very nice selection of stop words. So we're going to go back and use spaCy to help us out here. Since spaCy focuses more on natural language processing, it's going to focus more on that field. So within the English language, there's stop words. And of course, if you install other modules, you're going to have respective stop words for that language. So let's go ahead and investigate some of these stop words. Import stop words. Let's see what type. We import stop words. We might be wondering, what is the data type for this variable? So we're going to print that out. What we notice is that the data type for stop words is a set, which makes sense because that's sort of a natural way, a natural data structure we use for a collection of unique words or unique elements, unique entries. So we're going to make use of a set. For our analysis, what if we wanted to go ahead and add the word Python? We want to not count the word Python in our word usage classifier. So we're going to go ahead and use the union method of our set. So the union method is going to accept another set. So we're going to create another set here. Notice the curly braces. And that's going to return a new set object. So we'll call that stop words Python. Print that out. We see the set of all the stop words. So if we examine this set, we're going to see things that we understand aren't going to be very useful in our counting process. There's no need to count that word. Things like about, a, across, after. You get the point. Counting these words aren't going to contribute any signal. They're just going to add noise to our process. And what I recommend is that go ahead and examine these words. There are about roughly 300 of them, because there might be, maybe there's something weird and you want to include that word, you want to count that word. In fact, if I look at here, let's do some analysis here. Let's see if the word computer is in here. So since it's a set, I can easily do membership checks. So I say computer in stop words. Oh, so it looks like computer isn't in there. I believe it used to be in there. Let's see, oh, this should be case lowercase. Let's see anything else. Let's say language. Is language in stop words? Well, that's false, so it's not in there. That's good, right? Language is probably going to be a very important word, a very important feature for our task. So we have the word 6 is in stop words. We see that there. Let's see if 7's in there. And 7 is not in stop words. It's a little weird. So take a look at it, examine your stop words, and make sure that there's nothing in here that you want to not exclude from the analysis. It's only 300 words, so it shouldn't be too bad, too difficult to scan through. You can use the in statement to do membership checks. We are working with a set. So including stop words is very cheap. It's not going to really slow down our analysis. In fact, it can speed it up because there's additional words we shouldn't consider. Now, in our current analysis, words like Python and Pythons are going to be counted as distinct words. Since they're spelled differently, they're going to be treated as different features. And in fact, if we use a hashing vectorizer, since they're different words, they're going to result in a different hash value. So they're going to be treated as its own feature. So we have one feature that's Python, other feature of Pythons. Same thing as other words, tree and trees. Guess what? They're going to be counted as distinct words, as distinct features in our resulting matrix. But we understand that we don't want this to happen. Words like Python and Pythons, tree and trees, they represent the same concept. They represent the same word. This also extends to verbs. Let's say we have the verb run, runs, and ran. So different tenses for our verb. At the moment, these are all considered distinct words, distinct features. But we don't want that. They all represent the same concept, the concept of to run. So we want to fix this. We understand by fixing this, we're going to boost some of our model's performance. So let's consider historically an algorithm that was initially used for this processing. That's called stemming. And stemming is going to reduce a word to its stem. Now, stemming isn't 100% effective. It's an older algorithm. Usually follows a set of rules to reduce a word, to try its best to reduce a word to its stem. So something like a popular stemming algorithm is called the Porter stemming algorithm. And when you apply it to a word like argues or arguing, it's going to return the word argue, misspelled R-A-R-G-U. So stemming isn't always going to return a true dictionary word. It's a crude method, but it's rather effective, and historically was initially used because it was sort of the first attempt to fix this problem here. Now, one of the things I want to keep in mind with this here is that we understand that since we're working with English, the stemming and lemmatization we'll talk about here might have different effects with different languages. English, generally speaking, isn't a highly inflected language. Other languages, like Russian and specifically Latin, those are highly inflected languages. So we're going to see that our mileage might carry us further if we apply some of these techniques in other languages. But we're going to focus mostly on English here, but keep in mind that spaCy has tools for other languages. So stemming is a crude method. Isn't always going to return as a dictionary form of the word. What I want to do is I want to map multiple features into one single feature. A more sophisticated process is called lemmatization. Lemmatization is all about reducing a word to its lemma. Lemma is just a fancy way of saying the dictionary form of the word, the form of the word we would look up in a dictionary. If you want to understand what does the word running mean, we wouldn't look up run in the dictionary. We would look up its lemma, run. So I won't go into the exact algorithm that spaCy is using for lemmatization, but it's going to use some context of the word, how it's used in the sentence, in the document. It has some fancy algorithms it's using to identify what is the lemma of a word. Now, lemmatization is not going to be a 100% accurate process. It isn't always going to be correct. It might fail at times. So keep that in mind if you're using lemmatization. It's not going to be perfect. You can examine some of the results. You might be satisfied with them and go ahead and include it into your process. Let's go ahead and see how we can return the lemma of a word using spaCy. So here we're going to say we're going to construct our document using the NLP function here. Remember, the NLP function is going to take a string and analyze it, run it through a pipeline. So we have runs, ran, and running. So we're going to iterate through all the words in this process document. And each word, or what's called token in spaCy, has a attribute called lemma. Notice this ends in an underscore, so it's going to use that same convention in scikit-learn. This is something that I discovered, I calculated after running some analysis, some processing on the words, on the tokens. So the lemma attribute will return the lemma of that particular word. We'll go ahead and repeat the process for a different sentence, buy, buys, buying, and bought. So we understand that this all represents the same concept up to buy. So we want to make sure that it's going to return the exact same lemma. And we see saw, seen, and seen. So notice here I'm particularly picking some irregular verbs. Things that kind of break the pattern in English. Things that aren't so trivial. So let's go ahead and run the analysis. So we see the first example here. All those different forms of the word to run were reduced to the same lemma, to run. This is just run. Let's look at the buy, buys, buying, and bought. In this example here, 3 of the 4 were reduced to the same lemma, but it failed at buying. Didn't do a good job there. Like I said, this process of lemmatization isn't perfect, but you're going to get different mileage. So that's what you should always inspect to see how well it works. But the whole point here is, like, yes, it's not perfect, but perhaps it's enough to boost our model's performance. Let's look at see, saw, seen, and seeing. And there, 3 out of 4. That ain't bad. Isn't completely perfect. Now, one quick note here is that the less than perfect performance of lemmatization with this version of spaCy is a problem. But this has been fixed for newer versions. So at least the version we're using now, there is a bug, but newer versions will fix some of this situation. But nonetheless, we see here where lemmatization is helping out. Is it 100% perfect? But in future editions of spaCy, it will be perfected. Perhaps not 100% perfected, but closer to 100. Okay, so we talked about lemmatization. You might be considering, okay, so we talked about lemmatization. How can I incorporate it into my model? How can I incorporate it into my analysis, into my workflow? Well, let's look at a keyword argument for our vectorizers. Let's look at count vectorizer. There is a, let's see where I can see it. Where is tokenizer? Let's look at what that says here. Tokenizer, override the string tokenization step while preserving the pre-processing of n-grams generation. Okay, so that perhaps wasn't very helpful. But tokenizer, so token is basically what you're counting when we do natural language processing. And we can set the tokenizer to be a different function. What's going to happen here is that the tokenizer function is the function that the transformer is going to use to generate the tokens and generate the words it counts. What we want to do here is that we want to provide our own tokenizer. We want to provide our own function to take a document and break it down into the words it's going to count, into the things it's going to count. So let's play around with this. What I'm going to do here is let's just go ahead and comment things out initially so we can run some certain blocks of this code. So I define my limitizer. It looks like there's a problem there. Yes, forgot to comment these other lines here. Run that. Okay. Let's just try out this limitizer. Let's see how it works. And let's say I'm going to pass a string. Let's say the quick brown fox jumped over the lazy dog. Okay, so notice that it returned a string and returned the lemma of each of our words. So notice jumped is now just jump. There weren't too much verb conjugations there, so we didn't see too much of a power there, but let's just say dogs are running quickly. This is a better example here. Notice a word like dogs, it returns just dog. So the singular word of the singular form of the word are is the verb to be. Running is run, and quickly is still quickly. Okay. So that's what's happening here. We're examining the lemma. So now what we can go ahead and do is we can introduce this function into our vectorizer. One thing that is a gotcha is that if we're going to use lemmatization, we got to make sure that we lemmatize our stop words. So we're going to lemmatize our stop words. This would be a little bit tricky here. The reason why is because this NLP function is going to accept a string. So we got to make sure we take our set, convert it into a string of words, and then pass that string of words into the lemmatization process. So return the lemma of all those strings of words, and then create a set from those lemmatized words. That's a little two-step process there. We can break it down, see what's happening. So we generate the lemma of our stop words. We understand that's important because now we're counting lemmas. So we got to make sure our stop words are lemmas. In this example here, we're just going to say, just give me 100 features. In practice, you wouldn't really play around with max features, but we only want to look at the at 100 features. Give us the limit, the lemmatized version of stop words. The tokenizer is now the lemmatizer. In other words, use this function to break down our sentence, break down our document into the tokens that we're going to count. Okay. And since we're going to transform straight from the array of strings, the array of documents, we're going to use the vectorizer as opposed to the transformer. So we're going to use the TF-IDF vectorizer as opposed to the transformer. In other words, the transformer that encompasses both the counting process and the generating the TF-IDF weights. Let's fit our TF-IDF lemma transformer. Let's go ahead and get the resulting features. This might take a while because we have to lemmatize the words. We have to inspect each of the words. So it's a little bit of a slow process. So we go back to the idea of, you know what, perhaps lemmatization doesn't really improve in our performance, and is it really worth the longer computational time? We need to consider that for our application. So a lot of junk here, admittedly. But notice, we can see we have lemmas of words. So perhaps we can go back here in our lemmatization step and remove some of this junk. But nonetheless, we can see that we now have the lemmas of the words we are analyzing.